So we're continuing with your Cantor. By the way, all these lectures are getting recorded, and on Collab you can see the recordings. I think with very few exceptions, we'll try to record every lecture for you, just in case. And remember, occasionally we take attendance. Every couple of lectures we'll pass a roll sheet, sign your name. I think we did that last time. And that goes towards that 10% of the grade that's attendance. So you get 10% just for showing up. That's a really good deal. So back to your Cantor. That's where we left off last time. He showed that not all infinities are created equal. Some are bigger than others in a very precise mathematical sense. We're about to see that. We mentioned that in the book, around page 174, 175, 176, you can see some of this material that we're covering right now. The material in the book obviously is not sequential necessarily, as you can take it in many orders. So that's where this thing is, diagonalization and dovetailing, which is what we're doing right now. We mentioned the infinite hotel example. Question? Is this good? Let me turn on the volume. Is this better? Okay, thank you. Infinite hotel, all rooms are full. A new guest can go in the first room once everybody has moved one down. So that means a one-to-one correspondence between a set and a proper subset of itself. That can't happen for finite sets. For infinite sets, it can, and that's an example. An even more striking example is if you have an infinity of guests all coming in, wanting rooms, you can take every guest to twice its room number. That frees up all the odd rooms, and all these new guests go into all the odd rooms. Again, that kind of trick cannot be done with finite hotels or finite sets in general. With infinities, that's no longer a constraint. With infinite sets, they can be put into one-to-one correspondence with proper subsets of themselves. When you have an infinity of infinities, same deal. Now you have to be a little more clever. You have to go dovetailing through the lines back and forth, zigzagging around, and that's where all the new guests come in. Okay. And then we also showed that you can put the integers in one-to-one correspondence with the natural numbers, interlace them, zip them up like this, and then number them, 1, 2, 3, 4, all the way up. All the integers are here, none are missing. All the natural numbers are here, none are missing, and they're paired up. Nobody's unpaired, so that means there's just as many integers as there are natural numbers, even though the natural numbers are only half the integers in a sense, or only the positive integers. So again, interesting counterintuitive observations about infinite sets that don't apply to finite sets. And then we showed even something more striking, that you can put one-to-one correspondence between the natural numbers and all of the fractions. Even though every two natural numbers have an infinity of fractions between them, even if they're consecutive. So between 1 and 2, there's an infinity of fractions. 1 1/2, 1 2/3, 1 9/10, and so on. Yet, you can dovetail through all the fractions, number them, and once they're numbered, every green natural number is paired with a blue-red fraction. None are missing, none are left out. Any questions about any of that? So that's an example of a one-to-one correspondence between two infinite sets, showing that their cardinalities are the same. So again, means the cardinality of the natural numbers is the same as the cardinality of the quotients of the fractions, the rational numbers. Before Cantor, we didn't know this. It didn't occur to anybody. There seem to be so many more fractions and natural numbers that we thought, there's infinitely more fractions than the natural numbers. Wrong. Exactly the same cardinality. So it's very deep, counterintuitive even. And here we're skipping the duplicates. So duplicates is not even an issue. Anytime you have something like 3/3, which is the same as 2/2, which is the same as 1/1, skip all the other incarnation of the same fraction all the way out, and only take unique ones that you haven't seen before, so you can even avoid duplicates in terms of values. So that's not an issue. It's not about duplicates. Same result. Question? Most of the things in this course have very, very real applications. So for example, this can be shown, so dovetailing and diagonalization, the two techniques we're on now, can be used to show that certain problems are not decidable. There's no algorithms for them. So people throughout history have tried to solve problems really, really hard and couldn't. They didn't know why, and they kept trying. And they spent years, decades, and millions of dollars if they were a company. It turns out some of these problems are not solvable to begin with. There is no solutions to them in terms of algorithm. They didn't know that, so they kept trying and trying and trying for decades, for centuries, spending billions of dollars. Companies have done this, governments have done that. These two techniques can be used to show that some problems are not solvable. So when you run across one of those problems, if you can prove that one of those problems is unsolvable, you can save yourself centuries of manpower and billions of dollars and not bother trying to solve it because you know for sure an algorithm doesn't exist. How's that for practical problems? You can save you billions of dollars and centuries of labor. Very, very dramatic practical applications. And there's many other practical applications too, because these two techniques give you insights, all sorts of, not just whether it's solvable or not, but how easily solvable, even if it's solvable. And that gets into NP-completeness. And these techniques are used again and again all over the place for all sorts of applications, including very practical ones, involving dollars and cents and years of labor potentially saved. Okay, but it's always good. Always ask yourself, why am I studying this? Why is this important? Now, even if this wasn't practical, it'd still be very cool. But it's very practical on top of that. Good question. All right, so there's lots of ways to dovetail. You can dovetail across the diagonals like this and number them like that. That's okay. You don't have to go in a serpentine way. You can number them this way. It's fine. And here again, we're skipping duplicates. That's perfectly valid. So I want you to know there's lots and lots of ways of putting two sets into one-to-one correspondence. It's not a unique single way. Right? Just like there's lots and lots of ways to write a program that prints prime numbers. If each one of you wrote a prime number program, probably no two programs would be identical unless there was some copying. Right? There's no uniqueness about these kind of things. There's lots of things that could work. But there's lots of things that don't work, too. So be aware of that. So why doesn't this work? Why can't I number them 1, 2, 3, 4, all the way down this line, and then later number the other rational numbers on the second row, then the third row, then the fourth row, and so on? Why doesn't this work as a dovetailing technique? So I showed you two that work, and now we're seeing one that I'm telling you doesn't work. Why? Okay, but remember that in the Infinite Hotel, we have an infinity of infinities of guests in the lobby. We still managed to do it. And even here, we still have an infinity of infinities, and we still managed to do it. So, any other thoughts? Yeah. Why? Yeah, he's saying there wouldn't be a number for 2 over 1. You'll run out of numbers here. And he's right. Once you go 1, 2, 3, 4, 5, 6, 7, 8, all the way out, after the end of that, you won't be able to get to the second line. But the reason is even simpler, that you'll run out of numbers. Listen to my words very carefully. After the end of the first line, you'll get to the second line, and then you'll do something else. What do you say? There is no end. Just because I said end, that doesn't mean anything. You could always flap your lips and make noises. It doesn't mean there's meaning behind it. Again, a very important thing to remember as you go through life listening to people. There is no end. So if I say get to the end and then blah, 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 no, there is no end. You'll never get to it, and then there's nothing else you can do after that, because there is no after that, because there's no end. It goes on and on. Right? You have to be careful with words, semantics. There's an old children's joke, you're in a closed room, no windows, no doors, completely boxed in, but you have an apple. How do you escape from the room? Break the apple in two, take the 2 halves, make a hole, and then escape through a hole. But that's just a play on words, right? It's semantics, improperly construed, right? Just because you say certain words doesn't imbue reality to them, or common sense, or consistency. It's just noise. Keep that in mind. Very, very important life lesson, if you can abstract it enough. So you can't get to the end and then do something else simply because there's no end. Just because you said it doesn't make it so. Okay? So that attempt at dovetailing doesn't work. And there's many other attempts that don't work. And there's many attempts that do work. So now we see some of each. So you have to be careful about one-to-one correspondences. But 2 sets are the same cardinality if there's one that works. That's sufficient. Not all of them have to work, obviously. If one works, you're done. The two sets have the same cardinality. It's sufficient to prove that. All right, so more about dovetailing. So the example we saw before, we didn't call it dovetailing, but it is dovetailing, putting the integers into one-to-one correspondence with the rational numbers, with the natural numbers, rather, by interlacing them, right? Negatives and positives, blue and red. And that's an example of dovetailing because a dovetailing looks like this here. It's not a big serpentine thing in a plane. It's more like zigzagging across two adjacent rows. That's okay. That's still dovetailing. Dovetailing has many guises. It can appear in many ways. And sometimes it's not even geometric, where there's a nice line going through. It's more algebraic. You should define a rule how the matching occurs. That's okay. That's still dovetailing. So it doesn't have to be a physical geometric line, serpentine, snaking around. It could be many other things. It's still dovetailing. How many get this? All right, any questions? Things will build very heavily on these concepts, so wrap your mind very tightly around it early on. And if you have questions, ask right away. Here's another way to dovetail through these things. We're still trying to match the fractions, the quotients, to the natural numbers. So now I'm going to give you a rule, an algebraic rule. So sort all fractions by the sort key max of the absolute value of the numerator and the absolute value of the denominator. So x over y is going to be sorted in this long list by the max of whatever the x and the y is in absolute value, numerator and denominator. So if the max of the x and the y is 0, there's nothing. Right? Because the numerator cannot be 0. Excuse me, the denominator cannot be 0 because there will be division by 0. Y will be 0, division by 0. So that's the empty set for sort key 0. For sort key 1, you have a couple of things. You have 0 over 1 and 1 over 1. So all fractions whose absolute value, numerator and denominator, are at most 1 in absolute value. There's two things. Now, if it's 2, there's a couple of more things, 1 over 2 and 2 over 1. And, of course, the 2 from before. If it's 3, there's even more things than that. 1/3, 2/3, 3 over 1, and 3 over 2, and plus all these, where the max. So we're sorting this list of fractions by the numerator, denominator, max absolute value. How many get this? That's the sort key. Okay. Once we do this, we can number them. 1, 2, 3, 4, 5, 6. And there's your dovetailing. And that's different than the example we saw earlier in the plane. It's different than this or this. This is a different rule. And here, we had pictures. Here, we just have an algebraic rule. It's still dovetail, just without some nice geometric serpentine path. Okay, any questions about that? There's lots of other ways to do it. Yeah. Max? Oh, it takes a maximum of two things. So the maximum of x and y is whichever is larger. That's the answer. So the max of 2 and 3 is 3. The max of 3 and 3 is still 3. The max of 3 or 4 is 4. So the max of, just a maximum function. Takes two arguments, returns the larger of the two. That's all. Good question. Always ask about definitions or try to understand what the definitions are. Don't just move on. What else? All right. Now we're going to prove something even more amazing. When it comes to real numbers, there's more of them than integers or rationals. And that's even more counterintuitive than before. Why? Because any two consecutive integers have an infinity of fractions between them. So you think there's more fractions than integers. Because any two integers consecutive, like 5 and 6, has an infinity of fractions in between. So intuitively, people thought, oh, there's more fractions than natural numbers. But we just showed that there aren't, using dovetailing. So now you might say the same thing about the reals. Between any two integers, like 5 and 6, is an infinity of reals. And so maybe, just like before, there's now one-to-one correspondence possible between real numbers and natural numbers. And there isn't. You can't do that. What's the big difference? Right? Between any two fractions, there's another fraction. Prove that. In one sentence, prove to me that between any two fractions, there's another fraction. What's your argument? Take the average, for example, and many other examples. Between any two real numbers, there's another real number that's different than both. Again, take the average. So what's why is there more reals than fractions then? They both have this property of denseness. Between any two of them, there's another and another and another. They're both kind of dense, in a sense. If I ask you, what's the closest fraction to 0 on the positive side? What would you say to that? The closest fraction to 0, that's a positive number. What's your answer? Somebody else? Raise your hand. Feel the rush. You get points for bravery just for saying something. It's good. Good practice. Yeah. 1 over infinity. Any thoughts on that? What's the value of 1 over infinity? First of all, that phrase is not even well defined quite. It sounds like a limit. It sounds like 1 over n as n goes to infinity. And what's the limit of 1 over n as n goes to infinity? 0. So you're essentially saying 0. And 0 is not the closest number to 0 on the positive side. It's not even positive. 0 is not positive. So it doesn't quite work, but I appreciate you speaking up. That's good. Others should follow his footsteps. What else? Yeah. No such thing. There is no positive value closest to 0. Because, why? Prove that. So he's right. But give me another one sentence that proves what he just said. There ain't no such thing. Why? Yeah, again, the average trick. If there was such a number, take the average with 0, and that will be closer to 0. And so that wasn't it. And you can do that for any number that you can name. So there is no closest positive value to 0. It ain't there, amazingly enough. How about real numbers? What's the closest real number to 0? Not fraction, but closest real number to 0 that's still positive. Now, that should be easy. Same reason, ain't there. So both the reals and the fractions are dense in that sense, and no two are adjacent. The integers, the closest integer to 3 that's bigger than 3 is 4. It is there. It exists. I just named it. But the closest real number to 3, bigger than 3, ain't there. The closest rational number to 3, bigger than 3, ain't there either. They're dense. There's no two that are neighbors. There's always stuff in between of the same kind, strangely enough. Or maybe not so strangely. I mean, once you reason about it, it seems okay. It seems straightforward. So why are there more reals than rationals? They both have the same property of denseness, and between any two, there's an infinity of other ones, and we're about to prove this. So it's going to be a proof by contradiction. So if you want to show that there exists no one-to-one correspondence between real numbers and natural numbers, or fractions even, because now we know the fractions and the naturals are the same cardinality, so we can compare either one to the reals now. How many get that? We just show that the naturals and the fractions have the same cardinality by the dovetailing principle. So either one can be compared to the reals because it's the same cardinality. Right? The nice thing about one-to-one correspondence is if you compose them, you get another one-to-one correspondence. Same about permutations. If you can compose 2 permutations, you get another permutation. You compose functions, you can compose one-to-one correspondences. And you get more of the same. So it doesn't suffice to show that there is some attempt at one-to-one correspondence that fails. That doesn't cut it. Because remember, we tried that for things like this. We tried a one-to-one correspondence by numbering them like this. It didn't work because there was no n, so we never got to the second row, and this failed. But that doesn't mean there is no one-to-one correspondence that does work. And there is. It's just that this one didn't work. So just because one didn't work, it doesn't mean that there is no one that does work. You have to keep the logic straight, right? So to show that there's no one-to-one correspondence between the naturals and the reals, you can't just try to make a one-to-one correspondence, fail to do so, and then raise your hands in victory and say, it ain't there, because I tried and failed. Maybe somebody else will try and succeed. You have to show that none exists ever for you or for anybody else. That's a very tall order. It's a non-existence proof. All right. The whole thing will fit on one slide, but don't let that fool you. It's a very subtle argument. And here we go. Let's say towards contradiction, there was a one-to-one correspondence. And if there was, you can put them in one big table. All the natural numbers would be here, 1, 2, 3, 4, 5. Clearly, they're all there, starting with 1, 2, 3, all the way down. It's an infinite table. That's OK. And then let's assume that somebody omniscient put all the reals in this right-hand side of the table. So here's pi, here's 1, here's e, here's the square root of 2, here's 1/3, and so on. Doesn't matter what order. They get to choose the order. I'm just giving you an illustration of what these numbers might look like as real numbers on the right-hand side. So the claim is that all the naturals are there, and all the reals are there, and this is a supposed one-to-one correspondence. Never mind how. Let's just say it works. Some omniscient entity with infinite wisdom came up with this table, and that's their one-to-one correspondence. We're going to show that it doesn't work, no matter who constructed it, no matter how omniscient they were. And here's how. Go down the diagonal and construct a number that's formed from the diagonal. Start with a 0, and the first number here past the decimal point is a 1, so make that a 2. We're going to construct a number, a real number that's missing from this table. So that 1 becomes a 2. And that 0 becomes a 1. In other words, we're adding 1 to the diagonal. This 8 becomes a 9. This 2 becomes a 3. This 3 becomes a 4. Anyway, we add 1 to the diagonal. We get this real number here, x. And x is a real number. How do we know? Well, because here's the decimal point, and here's a bunch of digits. That's what a real number is in decimal representation. But x is a real number, and this real number is missing from this table. It's not on the right-hand side, no matter how cleverly it was constructed. Why? Because it's not the first row, because it differs from the first row by at least 1 digit. This here's a 1 past the decimal point. This here is a 2 past the decimal point. So it ain't the same number as the first row. It's not the same number as the second row. It's not the same number as the third row, because it differs by at least 1 digit, and perhaps many more digits, from any row in the table. So that x in red ain't in the table. It's not there. Which means that table cannot be a one-to-one correspondence. It's at least 1 missing real, and perhaps many more missing reals, but it's not a one-to-one correspondence as claimed. Which means this table is not a one-to-one correspondence, but this table was an arbitrary one-to-one correspondence constructed by some omniscient entity, guaranteed to work. And we just showed that no matter what, we can always find things that are not on this right column, because all the natural numbers are on the left column. 1, 2, 3, 4. That part is clear. And we just disproved that all the real numbers are on the right column, no matter how you try to construct a table like that, however cleverly you try to be. And so because this table was a general one-to-one correspondence, supposedly, towards contradiction, we just showed that it ain't. And so there is no one-to-one correspondence between natural numbers and reals, or equivalently between fractions and reals, because we already showed fractions and natural numbers are a one-to-one correspondence by dovetail. So there's more real numbers than fractions, is the bottom line. Much more. Amazingly enough. Question? Good. Excellent question. So she's saying, why can't you do the same trick with fractions? Why can't you populate this with fractions? In fact, populate it with fractions in a way that you number them here using the dovetailing. That will ensure that all the fractions are there. So now all the fractions are here in decimal form. Okay. And then construct this number here. And then show that this number here is not in a table, and so therefore there is no one-to-one correspondence between natural numbers and fractions. That's what she's saying. All right. Anybody want to address that? Maybe somebody who hasn't spoken yet today. Some fresh person. Where does this go awry? Yeah. Well, so this number is picked exactly like before. We go down the diagonal, add 1 to the diagonal, get this. That part is okay. That will work. Each fraction could be represented as decimal notation. Like here's this fraction 1/3 right there. So every fraction could be represented as a decimal notation, either repeating or terminating, whatever. If it's terminating, put zeros, pad it out with zeros. It's still decimal notation. Go down the diagonal, construct this, and then what? Yeah. Yeah, the number in red here that you created from the diagonal may not be a rational number. It may be pi or e or square root of 2 or the golden ratio or some other irrational number. And then it's no contradiction that it's a real number. It's just not a rational number. If it's not a rational number, it doesn't belong in a table, because the table now is all rationals on the right-hand side. And so there's no contradiction. So it's a very good question, and that's why this argument fails to show that there's more rationals than natural numbers, because this number you constructed here may not be rational. It's not guaranteed to be rational. It's guaranteed to be real, but not rational. This could end up being, pi over 10 or some other irrational number. How many got that? It's a very good question. Excellent. What else? Ask more questions. If you're not asking a lot of questions, you're not wrapping your mind very tightly around this, because this is very counterintuitive. This is pretty bizarre, actually. When Cantor first came up with this argument and tried to publish it, people didn't even believe it was math. They thought it was some sleight of hand, some trickery, some whatever. Today, most of theoretical computer science is based on these arguments of diagonalization and dovetailing, and a few more things. Turing based his entire work on this. Question? So, towards contradiction, we assume that all real numbers are there. So they're not all there. We assume that they're all there and prove that they can't be all there. So it's a proof by contradiction. Very good question. So it's not that they're all there. We say if they were all there, then there's one that isn't. So they can't be all there. That's the argument. It's a proof by contradiction. Good question. What else? Yeah. Oh, good. So he's saying this red number, why isn't it in the table? Because we assume that all numbers are in the table. Well, if it's in the table, it's got to be one of the rows of the table. So ask yourself, is it the first row? Is this first row? No, because it differs from the first row by at least the first digit. It differs from the second row by at least the second digit. It differs from the third row by at least the third digit. It differs from any ith row by the ith digit, and so it ain't any one of the rows. So it ain't there. Very powerful argument. Good question. It's not a long argument, but it's subtle. Question? The integers are a subset of the reals. They're a proper subset, because every integer is a real number, but there are real numbers that are not integers, like 1.5. And you can also show that the fractions are a proper subset of the reals. Every fraction is a real number, but some real numbers are not fractions, like pi and e and square root of 2. But to show that there are real numbers that are not rational, this could do it. But this doesn't give you an example of an actual real number that is not rational. This just shows you that there's plenty of them, but doesn't tell you what any one is. Just like prime numbers, it can show that there's a prime bigger than a googolplex, simply because it's infinity. So prime is bigger than any number. But try to come up with an actual prime bigger than a googolplex and write it down. That's a very different thing. Even though you know it's there, writing it down is not easy. But some things you can't write down, not because it's not easy, but because they ain't there. Just like trying to write down a fraction, an integer between a quarter and a third. It's not because it's hard. It's because it ain't there to be written by us or by anybody, even by an omniscient entity. They can't do it either. It's not a matter of smarts. It ain't there for anybody to do. I hope that makes sense. Yeah. Excellent question. I was waiting for somebody to ask that. Okay. So he's trying to cleverly make an end run around this. So he says, take this number that we just proved is not in the table, move everybody one down, make that number the first row, just like the infinite hotel. Put this guy in the first room, everybody moves to one room down. So the whole table now shifts down, this guy goes to the beginning. Is the problem fixed? Is it now on one-to-one correspondence? Yeah, because you can hit this table with the exact same trick. Find the diagonal of this new table, come up with a new number, not x, but y, and now this new number won't be in the table. And you can put the y in the table, move everybody one down, but now there'll be a z that's not in the table again by going down the diagonal. You see, you can always pull this trick, no matter how you augment the table or try to fix the table. The table is fatally flawed. It's permanently flawed. It cannot be fixed. using this trick or any other trick. So this is a non-existence proof. Very good questions. This is called diagonalization. We're going to use this argument again and again and again. Get a lot of mileage on this argument, so wrap your mind very tightly around it. You know, half the results of the course will directly or indirectly probably rely on this in one way or another, in some sense. And in fact, I have a slide on this. What if you take exactly what he asked? Take this number, put it first, and then move everybody one down. So that question was so good, I even was prepared for the slide on this. That's how good that question was. Doesn't work. You can still diagonalize and still get stuff. Here's a more subtle issue. So what if the number down here, x, was 0.9999999 repeated, which is really the same as 1. But the number 1.000 was already in the table. So even though the representation of 0.9999 and 1.000 seem different in decimal notation, they're the same value, namely 1. What about that case? Yeah. Yeah. So there's several ways to handle it. One is you can rearrange a table to kind of avoid this kind of duplication of representation. Another way is ask yourself, how often does this happen? How many ways can two real numbers have different decimal representations but still be the same mathematical value? Is there a third way to represent 1 other than 0.9999 repeated and 1.000 repeated? 1 at where? Good, because there's no end, so there's nowhere to put this other digit. So other thoughts? Is there more than 2 ways in decimal notation to represent a mathematical value? What do you think? Not necessarily a proof, you know. What do you think? How many say 2 is the max? How many say there could be a third, a fourth, a fifth way? Wow, nobody's voting. That's interesting. How many understood the question? I don't want to be presumptuous. All right, here's the question again. So 0.999999 repeated is really the mathematical value 1. 1.0000 repeated is again the mathematical value 1. So the mathematical value 1 has 2 different decimal representations. Here's one and here's another. My question is there a third? Different than the first 2. Representation in decimal of the same mathematical value 1. How many say yes? How many say no? Good, that's better. No, that's about it. This comes from below, this comes from above. You can think about it as a limit from below and a limit from above. And those are the 2 directions you can approach a limit point, from above and below. You can't approach it from the side, whatever that means. So there's 2 ways to represent numbers in decimal. I should say at most 2 ways to represent a value in decimal notation. And often it's unique. Pi, it's unique. Square root of 2 is unique. The only time you have this kind of behavior, think about it, is when? It's not just the integers, because you can have other places where you have repeated 9s and 0s. I'll let you ponder that. But you can avoid these kind of duplicates, or better yet, avoid the repetition. This kind of limit exists, this kind of problem exists only when you have a series of 9s after some point, or a series of 0s after some point, corresponding to the other case where it's 9s. So you can avoid 0s and 9s in this number, and then that would avoid this non-unique decimal representation of a mathematical value. So when you construct this x down here, what you can do is add 1 to the diagonal, but avoid 9s and avoid 0s, so you don't have this repeated stuff going on. So if it's an 8, don't make it a 9, make it a 7 instead. And if it's 9, don't make it a 0, make it an 8 instead, or some other number. It doesn't matter. So avoid recurring 9s and recurring 0s down here, and you have a lot of leeway how to construct this, so it's possible and, in fact, easy to do. And then you won't have this problem. How many sort of understand what I just said? Okay. Maybe we'll leave it at that. Yeah. So he's asking why is 0.99999 the same as 1? Several ways to argue that. One of them is it's really a limit, right? It's the limit of 0.9, 0.99, 0.999, and so on. It's the infinite geometric sum of 9/10 plus 9/100 plus 9,000 plus 9/10,000, and so on. And the limit of that is 1. Another way of saying it is subtract this number from that number. What is the value of this subtracted from that? Is it bigger than a half? No, it's smaller than that. Is it bigger than a tenth? Is it bigger than a millionth? No, it's smaller than that. Is it bigger than 1 over googolth? No, it's smaller than that. In fact, it's smaller than any positive number, which means it's 0. So the difference between them is 0. It's because it's smaller than any positive quantity. And there's even easier ways to prove it. So for extra credit, prove this some other way, other than what I just said. Prove, yeah. Well, in this case, yeah. No, because 0.333 is 1/3 and 0.4000 is 2/5, and those are two different numbers. So this only happens when you have 9s, not when you have 3s. Okay. Think about it some more. For extra credit, prove to be some of these things, one way or the other. That there's at most 2 ways to represent a real number. That 0.999 is in fact 1, mathematically as a value, and so on. You know, extra credit for any of that. Yeah. So you say, why can that number eventually appear down the list? Because the list is infinite. Well, ask yourself, is this the first number on the list? And no, because it's different from the first number on the list by at least the first digit. It's different from the second number on the list by the second digit, and perhaps other digits too. So it's not the first number, it's not the second number, it's not the third number, it's not the fourth number, because these are 2 different digits. It's not the 5th number on the list. It's not the millionth number on the list. It's not the billionth number on the list. It's not the googolth number on the list. It's not the googolplex number on the list. It's not the ith number on the list for any I, which means it ain't on the list. That's why. And I understand what you're trying to say. You say, well, there's so many of them, it's got to be one of those. No, it doesn't. Just because it's an infinite number, it doesn't have to be one of those just because there's an infinity of them. Just like if I wanted to say my right shoe is an integer. Sounds kind of silly, but let's see. And I can see it's the same. I can say, well, there's an infinity of integers. Maybe one of them is my right shoe. How do I know it ain't? Well, the first integer ain't my right shoe. The second integer ain't my right shoe either. The third is not. The millionth one, the googolth one, the googolplex one is not. But there's an infinity of other choices. Maybe one of them is my right shoe. No, they're not. Not any of them, even though there's an infinity of them. And the argument is simply by type. Right? The millionth integer is a number. My right shoe is not a number. It's a footwear by type. It's a shoe. So if the type of 2 objects is different, the object cannot be the same no matter what else is true. If the types mismatch, the object cannot be the same. If the types match, doesn't mean the objects are the same either. Right? You can have 2 integers, 4 and 5. The types are the same. They're both integer, but they're still not the same object. One is a 4 and one is a 5. They're different. But if the types are different, one is a number and one is a shoe, forget about it. They're not going to match no matter what. The type is wrong, among other things. So I'm not being facetious when I talk about shoes inside the integers. If I say, find me a shoe inside the integers, it's not a matter of omniscience. If you take an omnipotent, omniscient entity and ask them to find the shoe in the integers, they won't be able to do it either. It's not a matter of smarts. You have infinite wisdom that still will fail to find a shoe in the integers. Now you might say, well, if the entity is omniscient and omnipotent, maybe they can will the shoe into the integers. Now you have an integer with a shoe in the middle of them. Well, but now it's not the integers originally. It's been modified. Integers plus a shoe. So it still fails on the original set of integers. So non-existence proofs are very powerful when you can muster them. Any other questions about this? And in the rest of the course, we'll come back again and again to these concepts with a vengeance. So welcome to infinity, my gift to you. And this is at the tip of the iceberg. There's a whole study of infinities, and it turns out there's an infinity of infinities. So now we saw at least two kinds. The natural numbers, which is the same as the quotients, the rational numbers. Now we saw the reals, which are bigger. And the question is, are there infinities bigger than the reals? The answer is yes, they are. In fact, the power set of any set is bigger in cardinality than the set itself, including for infinite sets. So you can think about the reals as the same cardinality as the power set of the integer. What is the power set, by the way? I don't want to be presumptuous. What's the power set of a set? The set of all subsets. Okay. So the set of all subsets is always bigger than the set itself. You can prove that. In fact, for the first problem set, there's a problem that asks you to do exactly that. Prove that the power set is bigger than the set in terms of cardinality, including for infinite sets. It's certainly true for finite sets. Prove it to me easily for finite sets, that the power set is bigger than the set itself. Why is that true for finite sets? Yeah. So why are there more subsets, say, of 10 elements than there are elements in that 10-element set? Why are there more than 10 subsets? I guess you're saying it, but yeah. So any element could be taken as a singleton sets, like just one, and there's another set 2, and another set 3, plus the empty set, like you said, that will be the 11th set, plus a whole bunch of others that have more than one, so there's more of them. In general, how many subsets are there for k elements? If you have k elements in a set, how many subsets are there in general of any cardinality together? How many different subsets are there? 2 to the k. How many see 2 to the k? How many can prove 2 to the k? All right. Somebody different argue why it's 2 to the k. I have k elements, and I'm forming all subsets. Why is it 2 to the k different possible subsets, all distinct from one another? Yeah. Yeah. So each element of the k, you can either take it or not take it. Take the second element or not take it. Take the third element or not take it. And once you're done taking or not taking every one element of the k, that's a subset. And if you don't take any of them, that's the empty set. If you take all k of them, that's the complete set of all of them. And anything in the middle is some combination. And how many different combinations of take or not take k times? It's 2 times 2 times 2 times 2. K times is 2 to the k. So there's 2 to the k ways of taking or not taking any one of k elements. 2 times 2 times 2. Because taking or not taking is a binary choice. Either you take it or you don't take it into your subset. How many get this argument? Okay. And that's why there's 2 to the k subsets of k elements. And in general, 2 to the k is bigger than k. Even for 0, it's bigger. Why? K is 0, 2 to the k is still bigger than k. Yeah, because 2 to the 0 is still 1, but 0 is still 0, and 1 is bigger than 0. All right, so more generally about non-existence proof, and we'll see lots of non-existence proof in this course, and we'll see a lot of existence proofs too. Non-existence proofs must cover all possible scenarios, and there's usually an infinity of scenarios. You have to cover a lot of ground, right? You can't just give one counterexample that doesn't work. You have to show that no possible example will ever work, and that's a much taller order for non-existence proof, right? It's not symmetric to existence proof. It's not just taking an existence proof and flipping it around and using the same logic. That doesn't work. Let me give you an example from real life. Let's say you want to prove to somebody that you're a millionaire. Never mind why, you just need to do it, okay? There's lots of ways you can show it. You could show that in your bank account, you got a 7-digit or more balance, and it's your bank account, your name is on it, fine. That's a proof that you're a millionaire. You own that money fair and square, it's in your bank. Lots of other ways to prove that. You could prove that, this is your house, and this kind of house with its own private beach on its own little island probably costs more than $1 million, and if it's yours and you have the trust deed, your name is on it, fair and square, legally, it's all paid off, you're a millionaire, fine. That's another kind of proof. Or you can just show me the money, like Jerry Maguire says. In your basement, you may have a big stack of cash. They can go and count it. It's a few $1 million. It's yours, assuming you didn't steal it and the police is not after you, whatever. Okay, that's another kind of proof. Easy to prove you're a millionaire. Lots of ways to do it, very convincingly. Okay, switching to the other scenario. Let's say you're trying to prove that you're not a millionaire. How would you do it? Can you just flip one of these proofs around? Can you just show a balance in your checking account of $3 and say, look, my checking only has $3 in it, and therefore I'm not a millionaire? Are you convinced? Would you bet your life on that? What's wrong with that argument? Yeah, I can have other bank accounts. All right, so let's say I show you all bank accounts in the whole world. Never mind how I managed to do this. I give you a long list of all billions of accounts everywhere. I say, look, none of them have my name on it, and the ones that do have only a few bucks in it, therefore I'm not a millionaire. QED. Are you convinced now? Yeah. Yeah, you can have all sorts of assets. You can own properties. You can even own things under assumed names. Maybe you won the lottery and that ticket hasn't been cashed yet. Maybe you have a will coming to you from some rich relative that hasn't quite gotten the money to you yet through the estate lawyers or whatever. There's going to be lots of ways you can be a millionaire. And pretend that you're not. And there's no way to cover all this ground. So if you say, okay, here's my house. I live in a shack. Does that prove that I'm not a millionaire? In other words, flipping this existence proof to this non-existence proof, supposedly. So if you show that this is your house, that's where you sleep every night, does that establish that you're not a millionaire? No. Maybe you just like to rough it. Who knows? Whatever. You try to slum it for a while, for whatever reasons. Or you could say, if this is my car, it's only worth $5, or probably close to the real value of this thing. That doesn't establish that you're a millionaire. So there's nothing you can prove. You can show as an example or a piece of evidence that you're not a millionaire. You have to cover incredible amounts of ground, and even then there could be doubts whether you're not a millionaire. So proving that you're a millionaire is relatively easy. One example will do it. Proving that you're not a millionaire, it's hard to imagine how you would even do that. It will not be very convincing to your friends, and neither will it be to the IRS. So it's not just the flip side. You can't just take one proof and flip it around just easily. In here, you use one example. Here, you just show that no example works. It's a much, much different thing, and it's much harder. So existence proofs can be easy. I'm not saying they're always easy, but they could be as easy as show me the money. Non-existence proofs are often very hard. Again, not always extremely hard, but typically much, much harder than existence proofs. Because not showing you the money doesn't cut it. Showing you the money cuts it for proving I'm a millionaire. But not showing you the money doesn't cut it for proving you that I'm not a millionaire, because maybe I have other assets. Maybe I have gold bullion. Maybe I own a moon of some planet by whatever strange legal science fiction kind of scenario that may entail. Who knows? You have to cover a lot of ground. So the problem of P is equal to NP is one of those. That's why it's so hard. That's why it hasn't been solved for 50 years. It may not be solved for many more centuries, potentially. We don't know, because you have to show that no algorithm, no possible algorithm, no matter how clever or convoluted or long or complicated or sophisticated, will be able to solve certain problems like satisfiability or traveling salesman or one of those NP-complete problems. It's a non-existence proof. Those are usually much harder. Okay. All right, a little bit more about Cantor. So he invented all sorts of interesting sets that before him we didn't know existed. So here's one interesting example. Take the unit segment, remove the middle third. Then take the remaining two segments, remove their middle thirds. Remove the middle third here, and remove the middle third here. So each iteration removes the middle third of all the remaining segments from the last iteration. Right? So recursively, you remove all the middle thirds of all the remaining segments. And keep doing this forever. The question is, what's the remaining points, if any, that remain after this infinite number of removing middle thirds operation over and over again? How many understand the definition of this set? Okay, take a segment, remove the middle third, then remove the middle third of these two thirds, then remove the middle third of these two ninths, and then remove the middle third of these two 1/81sts, and so on and so on. Remove the middle third of all the segments. Keep going. At the end, what do you have left? And you might be tempted to say, nothing. It's empty at the very end. Take this to the limit. And it's not empty. For example, the endpoints always remain. For example, the first point 0 and the last point 1 always remain throughout this process. How many see that? In fact, a lot of endpoints of segments remain. So an infinite number of points remain after this limiting infinite process. The total length removed, amazingly enough, is 1/3 plus 2/9 right here, 1/9 and 1/9, plus 4 over 81st, and 4 over 27, and 8 over 81st, and so on. If you add it all up, the total length of all the segments removed is 1. So you remove the total of length 1 sum of segments, and yet you didn't remove everything. There's an infinity of points remaining. And whatever remains doesn't contain any solid intervals. It's a cloud of points. It's a fractal. That's another interesting observation. But it's not empty. We already mentioned that the endpoints are there, among many other points. And the number of points that remain is not even countable like the integers or the rationals. It's uncountable like the reals. So not only it's infinite, it's uncountably infinite. Countably infinite means you can count them like the natural numbers, one-to-one correspondences. Uncountable means the reals or worse, or bigger in cardinality. And an uncountable number of non-endpoints also remains. So like the example, that 0.14 is still there even though it's not an endpoint. It's not just endpoints that remain, it's non-endpoints that are there too, in uncountable quantities. And it's a totally disconnected set. There's no connected subsets. It's self-similar, it's a fractal. It has fractal Hausdorff dimension of 1.58. If you're not sure what that means, look up fractals and fractional dimensions. Certain objects can have a dimension of not 1 dimension or 2 dimensions or 3 dimensions. They can have an arbitrary fractional dimension. They have a dimension of 1.5 or 2.3 or something strange. Dimensions is not just an integer, it could be a real number, non-integer real number. If you didn't know that, look it up. So this set is a closed, totally bounded, compact, complete metric space with uncountable cardinality and Lebesgue measure 0. Tried to say that 5 times fast. We had no idea that such sets exist with this strange combination of properties until Cantor showed us an example, and there's one. And there's many other examples. And here's the name of Cantor shown as a Cantor set, which I thought is pretty cool. And you can generalize it to 2D. So if you take this Cantor set, cross it with itself, you get a so-called Cantor dust. Now you get a 2-dimensional version of this 1-dimensional Cantor set crossed with itself. And you can cross it 3-dimensionally and get a Cantor sponge, or however you want to think about it. So with that in mind, here's a Cantor omelet. And it's all pretty cool. So you can see why he sort of started going crazy towards the end of his life. This is really esoteric stuff. In the 1800s, it was pretty bizarre. Even his mathematician colleagues couldn't see exactly the depth and the subtlety and the wisdom and the beauty of all this. They kind of shunned it and were suspicious of this, and it kind of ran afoul of conventional mathematics. He had problems getting published. Today he's a hero. Turing based all of his work on Cantor, and so did many other people. They worked beautifully. So there's Cantor sponge, which is the Cantor set crossed with itself 3 times. And it has all the same properties that the Cantor set has as well in 1D. It all translates into arbitrary dimensions and so on. Any questions about any of this? This is the tip of an iceberg. If you want to read more, look at the book 1, 2, 3 Infinity, or the Infinity in the Mind by Rucker. That's the one that's on the class website. I think it's one of the required readings. Easy to read, beautiful insights. It'll blow your mind. Yeah. What's that? Who did he base his work on? Influence him? He's asking who influenced Cantor the most. So his work was so esoteric that it almost stands on its own. But basically, John Venn, who did regular set theory, normal set theory that we know and love, like things about subsets and unions and intersections and power sets and so on. So he took that and basically extended it to infinite quantities, to infinity. So I guess probably John Venn, of Venn diagram fame, I would say was sort of the the starting point. But he took it so far out that it really is monumental and stands by its own. You know, it's just a phenomenal mental feat to tell the rest of us humans that not all infinities are created equal. I mean, it doesn't even sound right. Even today, it doesn't sound right. So, you know, to tell you that there's infinities bigger than other infinities. I mean, infinity is already infinite. How could it be bigger than that? Well, this is how, because there's no one-to-one correspondence. And you can prove it using diagonalization and so on and so on. That's how you get bigger infinities, among other ways. Even today, it sounds wrong, except that it's true. All right, so but Bertrand Russell, early 1900s, he did so many things, it's unbelievable, including winning a Nobel Prize. And he authored Principia Mathematica, which basically took all of mathematics and put it on the foundation of set theory. He basically showed that set theory is sufficient to do any other kind of math you want, including calculus and algebra, geometry, and everything else. Set theory doesn't seem like it's enough. You know, in sets, you just have elements and little parentheses, braces that show you, sets and unions and intersections. How can you do calculus just using sets and elements? Well, he showed how, using Principia Mathematica. So he axiomatized all of mathematics on the back of set theory. So set theory, in some sense, is the machine language of mathematics. Everything can be done using it and it alone. We had no idea. We thought set theory was just a small piece of mathematics, and there's other, even more important pieces, like algebra, calculus, geometry, and so on. He said, no, all these reduce to set theory. Set theory is enough to do any math you want. Amazing. And it took him thousands of pages to prove this, by the way. And that's this whole 3-volume Principia Mathematica treatise that he wrote showing all of this. He also originated so-called Russell's paradox. He was also an activist, humanitarian, pacifist. He talked about stuff that today may seem more obvious, but back in the day was radical thinking and got him a lot of flack. He talked about stopping war and stopping nuclear stopping nuclear proliferation, and he talked about birth control and gender and racial equality, gay rights, back in the early 1900s, where he got a lot of crap for it. Even today, you get some crap for it, if you're in the wrong circles. But back then, it was monumental, the stuff that he pushed, in terms of societal issues, not just the mathematical stuff that he did. And he mentored and influenced other giants like Wittgenstein and Gödel and Turing and others. And he laid the foundation for all of computer science theory and won the Nobel Prize in Literature in 1950 just as a sideline. So here are some books by Russell, just to show you the diversity of topics that he pioneered and wrote about and investigated and thought deeply about. So he talked about education, logic, freedom, about religion and science. He talked about philosophical development, even a book on marriage and morals, books on all sorts of aspects of philosophy. Here are some more books by Russell. And when I say by Russell, I mean by Russell. These are not books about Russell. These are books by Russell. He wrote these, all of these. He wrote hundreds of things. You talk about democracy, about free will, about religion, about politics, about relativity theory, about skepticism, all sorts of things. Here are a few more books by Russell. I mean, he was really an intellectual giant. And in the context of our course, he pioneered the techniques that then Turing and Gödel and Church built upon to usher in all of theoretical computer science. And here's an excerpt from his Principia Mathematica, just to show you how tedious it is to put all of mathematics on the back of set theory, show you that set theory are the subroutines from which all of mathematics is built. Here's page 379 into the treatise, saying that a bunch of stuff, and then from this proposition, it will later follow that when arithmetical addition has been defined, that 1 plus 1 is equal to 2. It took us 379 pages to get to this conclusion, that 1 plus 1 is equal to 2, using sets and sets only. So he's building arithmetic slowly, excruciatingly, from sets. And sure enough, later in the next volume of the treatise, he sticks to his word and proves that 1 plus 1 is equal to 2. And he says the above proposition is occasionally useful That's an understatement. But it's perfectly serious. And then it keeps going and going and going, and at the end, all of math reduces to set theory. We had no idea that that's the case. And there's a website on the web where you can actually type in some expression, and it'll give you the complete Principia Mathematica derivation of a simple statement. So this one is actually 1 + 1 = 2, and the website gives you a live proof where you can click on all these and show you, lemmas and the reasoning why each line follows from the last, and so on and so on. So this whole Principia Mathematica is kind of live implemented as a JavaScript kind of website. It's kind of cool if you want to actually go through it for extra credit. Here's that 1 + 1 = 2 finally popping up. And he gets a lot of credit for a lot of stuff. Here he is getting the Nobel Prize from the King of Sweden, and there's another guy down here. Anybody recognize him? He has a UVA connection, actually. Another guy that got the Nobel Prize in 1950 alongside him the same year. Anybody can take a guess who that is? It's Faulkner, also for literature. Here he is marching in anti-war rally in the early 60s. Again, very interesting ideas that he had. Here is on an LP record, a vinyl record. Him and Einstein put out a record explaining, it's basically a lecture on the record, saying, notice to the world, renounce war, perish. Basically, they're talking about why war is a really bad idea and why it could be the end of the human species, especially when nuclear weapons are involved. And it's kind of a warning to the world, and this was in the early 50s, and of course, we're still not out of the danger zone yet. Nuclear proliferation is still a big issue, and it's a bit less of an issue today that the Cold War was over, but there's a Cold War, it's in recent years started up again with Russia and other nations, and North Korea and Iran, and we're still sort of in the same state that we were 50, 60, 70 years ago. And so here are the two biggest intellectual giants of the era, Einstein and Russell, telling the world that, war is a bad idea, especially nuclear war, and we haven't gotten much past that, in the last 70 years, sadly, but hopefully things will get better, not worse. So he gets a lot of credit for his contributions, and he famously said most people would sooner die than think, and in fact, they do die before they think. So here's Russell's paradox. It was invented around the time that he sent this thing for publication. The Principia Mathematica volume of treatise was in the press. And somebody said, okay, define the set of all sets that do not contain themselves. Because certain sets can contain themselves as elements. That's okay. You can have a set. First of all, you can have sets containing other sets. You can have a set containing the first element being the set of integers, the second element being the set of the reals. The third element could be the number pi. So it's 3 elements, the set of integers, the set of reals, and pi. And together as a set, it's a bigger set. So sets can contain sets as elements. How many get that? No big deal, right? They can contain anything as elements, including other sets. Once you get this realized, you can see that sets can contain themselves. So a set can contain the element pi, the element 0, and the third element will be the set itself. Now, it's a recursive definition. It gets nested all the way down. But that's okay. You can do that. How many see that leap? Okay. Just like in computer science data structures, you can have a pointer of a data structure that points to itself. That's okay. Why you'd want to do that is a different story, and there's actually cases where you do want to do that. Once you can see that sets can contain themselves, you can define the set of all sets that do not contain themselves. Because certain sets contain themselves, others don't. The set of reals do not contain themselves. The set I mentioned earlier does contain itself as an element. So you can define the set S containing all subsets T, or other sets T, such that T is not an element of T itself. T does not contain itself as an element. And this may seem like an innocuous definition. After all, it's very short. It seems very straightforward. But it raises an incredibly convoluted paradox. Because then you might ask yourself, does S contain itself as a member? Does it contain itself as an element? And if it does contain itself as an element, it doesn't. And if it doesn't, it does. Because if it contains itself as an element, it doesn't satisfy this definition. Because this says it must not contain itself as an element, so it won't appear as one of those T's. So if it contains itself as an element, it can contain itself as an element. If it doesn't contain itself as an element, it satisfies this, and then it must contain itself as an element. So it's an if and only if contradiction, right? S contains itself as an element if and only if it does not contain itself as an element. And there's lots of other ways to express this contradiction as well. Right? So for example, there's an old logic paradox about a town where there's a barber who shaves exactly those who do not shave themselves. It sounds pretty straightforward. The barber just shaves everybody who doesn't shave themselves, except if you ask yourself, does the barber shave himself? And if the barber shaves himself, his job is to shave exactly those who do not shave themselves. So if he shaves himself, he shouldn't shave himself. If he doesn't shave himself, he must shave exactly those that do not shave themselves, including himself. So if he doesn't shave himself, he must shave himself. So the barber shaves himself if and only if it does not shave himself, which is, again, the same contradiction, the same paradox, a disguised Russell's paradox. And there's many, many other ways to express this paradox. It's very fundamental. You can't get away from it. Here's another way of saying it. This sentence is false, period, quote unquote. If this sentence is false, what it says must be false. And what it says is false, which means what it says is true. So if it's false, it's a true statement, because it's speaking truthfully about its falseness. So if it's false, it must be true. But if it's true, it's false, because it doesn't say it's true. It denies its truth. So if it's true, it's false. So the sentence is false if and only if it's true. How many get this? It's a paradox. Very, very similar to all the other ones, just in different guises. Another way of expressing this paradox is saying, I am lying. If I'm lying, by saying I am lying, that sentence is a lie, then the contrary of it must be true, namely that I'm not lying. But if I'm not lying, I'm telling you the truth by saying I am lying. So I'm lying if and only if I'm not lying. Again, paradox. Is the answer to this question no? Again, paradox. The smallest positive integer, not describable in 20 words or less. If there was such a thing, here's a description in less than 20 words. So again, a paradox. So this kind of threw off Principia Mathematica. Russell himself was caught by surprise by this relatively straightforward paradox that nobody thought about before. And it kind of put logic and all of mathematics in some negative light or potentially inconsistent light, because this paradox is not easy to resolve. There's an old Star Trek episode from the 1960s where some robot comes on board, and finally the way Captain Kirk gets the better of him, it gives him Russell's paradox, saying, I am lying, and the robot goes in an infinite loop, and smoke comes out of his ears, and the Enterprise is saved. I guess you have to be a Star Trek Trekkie to fully appreciate it. But here's a more interesting, kind of straightforward rendition. Pinocchio saying, my nose will grow now. And as you know, Pinocchio, his nose grows if and only if he's lying. So if he says, my nose will now grow, and he's telling the truth, right? His nose will grow, but that means he's lying. That's the only time his nose does grow. But if he's lying, and he says, my nose will grow now, if he's lying, then his nose will grow, but if he's lying, his nose should not grow. And again, that's a paradox. So that's, again, a very cutesy way of capturing Russell's paradox yet again. So in some sense, this is a form of diagonalization. We won't harp too much about it, but if you think deeply about this paradox, there's self-referential aspects in it, and it's a form of diagonalization in some sense, without the actual diagonal, drawn out in a table, but it's a subtle form of diagonalization. And there's many, many other, ways of expressing it, in, some more humorous than others. Even in religious circles, there's always been kind of ancient debate about, if you have a deity that's omnipotent, that deity can do anything. So can that deity create an immovable object? Immovable object. Because he can do anything, so he should be able to create an object that nobody can move, including themselves. But that deity is omnipotent. And there's nothing that deity can't do, so if there's an object, he should be able to move it. But that object was supposed to be immovable. So either he cannot create an immovable object, or not be able to move it once it's created. Either way, there's something they can't do. So they can't be omnipotent after all. Again, Russell's paradox in the religious context. So we owe this guy a lot. And This brings us to a few other fellows you should hear about. When I say fellows, most of them were men, sadly. There was only a few women involved in mathematics in those days. Now there's a lot more, as it should be. But anyway, Hardy, a mathematician, wrote Mathematician's Apology, a nice kind of popular book that got a lot of kids interested in mathematics. So he's kind of almost like what Lewis Carroll did for kids. But by his own account, his most significant contribution to mathematics was discovering the mathematician Ramanujan. So that brings us to Srinivasa Ramanujan, who died young in his early 30s, and one of the greatest mathematicians who ever lived, real protege. So he lived in India. He was very poor, and he got a hold of a book of theorems. The book was like just a list of theorems without proofs. It was like a mathematical summary of known theorems. And it's the only book he had access to because he was poor, and this is turn of the century, 1900 roughly. And he looked at all the theorems and convinced himself why each one was true or not, and he thought that's how you prove things. Basically, you come up with some mathematical statement that is true, and then you just write it down. He didn't realize you have to have a proof and a logical argument and a QED at the end and a succession of steps and so on. And so he started writing down other theorems that he thought were true. And he did that by the hundreds. And at some point, he wrote to Hardy, who was in Cambridge at the time, England, and he said, here are some theorems that I came up with. He sent a list of several hundreds. And Hardy looked at that and his colleagues in Cambridge and thought it was a big practical joke, because about half the theorems that Ramanujan said I came up with were already known. They were just not in the book that Ramanujan actually had access to. But the other half were not known. And Ramanujan didn't provide proofs. He just wrote down things that he thought were true. And in most cases, he was right. And some of those theorems that he said were true, that were not known in the West, not only were they unknown, nobody's ever seen anything of that form before. The forms were bizarre. And so Hardy realized that either this guy is an incredibly elaborate prankster of amazing proportions, or a mathematical genius. It turns out it was the latter. And this guy influenced almost all the other fields. There's an entire journal to this day devoted to his work, the Ramanujan Journal. And if you want to, on a reading list, there's a book called The Man in New Infinity about him and his work and his contributions. And there's entire conferences and journals today still examining his work. My brother is a pure mathematician, algebraic number theorist, and for his PhD thesis, he proved a few things that Ramanujan wrote down as true, but never provided proof. And this was almost 100 years later. And so people still today are struggling to prove things that Ramanujan just wrote down. And very, very few times was he ever wrong. Almost unheard of. So it's really incredible. Here's a lecture on Ramanujan's Lost notebook. One of his notebooks was just discovered some years ago, just a few years ago, 2009, and some people are still making careers on his work and analyzing his stuff. To show you how intimately he was familiar with numbers, once Hardy relates that Ramanujan was sick in the hospital. Hardy visited him, and to try to cheer him up, he said that he rode a taxi cab to the hospital whose number was 1,729, and Hardy said that that number seemed to be kind of a dull number and not a very interesting one. And Ramanujan, from his hospital bed, immediately said, no, that number is pretty interesting, actually, because it's the smallest number expressible as the sum of two cubes in exactly two different ways. He just happened to know this. That's just how his mind worked. And that number is also a Fermat near miss. So it's not the sum of cubes. It's a sum of cubes in two different ways. So there's all sorts of interesting stories about him. It's become apocryphal. And let me just show you some of the formulas and theorems that he proved, or rather that he wrote down as true, but it didn't prove, but were just true. And other people have proved it and later on. So Ramanujan said that 1 over pi is equal to this. Infinite series of 4k factorial plus blah, blah, blah. I mean, look at the sizes of these integers and the complexity of this expression. And this is not an approximation to 1 over pi. It is 1 over pi. It's equal to 1 over pi. It's not about approximately 1 over pi. People in the West never have seen at the time expressions of this form. Here's a few more. Infinite integrals, infinite fractions, all sorts of equalities involving repeated sums. And if you saw the movie Good Will Hunting, how many have seen this? The character of Matt Damon is based on Ramanujan, actually. Him and Ben Affleck, when they wrote the script and won an Oscar for this, so did Robin Williams win an Oscar for supporting actor. They based it on Ramanujan and his life. Any questions so far about anything? We'll pick up on this next time. See you. Pi is finitely describable. Yeah.
Pi is.
Yes, of course. Here. Oh. So pi is the